As promised in our last class on energetics, energy involved in chemical reaction, today we're dealing with chemical kinetics, the rate of chemical reaction. What are the factors that affect the rate of chemical reactions, and what are the conditions that must be fulfilled before chemical reaction can take place? In every chemical reaction, we have reactant and product. We can simply say the rate of chemical reaction is how fast a particular reaction occurs. In chemical reaction, reactants are used up and products are formed. So chemical reaction or rate of chemical reaction can be expressed either in terms of the rate at which the reactants are used up or the rate at which the products are produced. Now let us show it visually. What happens to the amount of reactant and amount of product? So when you use the word amount can either be in form of mass, it can also be in form of concentration or volume. So if you have to use mass, so for the reactant, the mass of, as time goes by, when you talk about rate, it means you are dealing with time. As time increases or as time goes by, the amount of the reactant should drop, the mass should decrease. If it's volume of gas, if it's gas, we use volume, should decrease. If it's a solution, we use concentration. So the rate of chemical reaction mathematically can be expressed as what? The rate at which the mass of the reactant decreases, or the rate at which the mass of the product what? Increases. If it's a gas, volume, but most times we use concentration. Most times to express rates we use what? Concentration. So we can say the rate at which the concentration of the reactant decreases per time, it will decrease. If it's product, it will what? Increase. So product increase, reactant decrease. And what happens here? You can say the unit is reactant in mole per dm cube. So you can say the unit is what? If you are using concentration, mole per dm cube per time. So the time can be seconds, it can be minutes, it can be hour, it can even be days, depending on the nature of the reaction. But using the SI unit of time, seconds. So you can say mole per dm cube per seconds is the unit of what? Rate of what? Chemical reaction. Now let's suppose the initial amount, or let's say the initial concentration of the reactant, or a particular reactant. In this case, we have to focus on a reactant and product. Here we have two reactants. So it's either you focus on one of the reactants or one of the products. So you pick one when our one is used up. So suppose this is the initial amount of the reactant. Here, when at the beginning of what? The reaction, when time is 0. So what happens? The amount will decrease, but not linearly. It doesn't decrease linearly. Why? Because rate of chemical reaction, let me use R to represent it. So this means rate of chemical, let me write as T. The rate of chemical reaction is proportional to the concentration. As we have it here. Concentration. It means the more the concentration, the more the chemical reaction, and the lower the concentration, the lesser the chemical reaction, the rate of chemical reaction. Or better still, since we are scratching against time, the rate of chemical reaction and time, they are inverse proportional to time. It means the more time it takes for a reaction to occur, the lesser the rate of reaction. So reaction and time, they are what? Inverse proportional. So we have sketched the rate of chemical reaction to time, we are going to get something like this. So this will happen. So the reactant we use up from the initial value until it reaches 0. The product initially, at the beginning of the reaction, the product has no, there's no product form at all initially. So but with time what happens, the amount of product increases until it's become stabilized. So this represents the concentration of the reactant and it reduces the time, and this represents the concentration of what? Of the product, and it increases with time. Like I said, it can also be volume or mass. So if it's mass, they need to be what? Mass per, that will be grams per second. If it's volume, that will be what? Cm cube per second. If it's concentration, mole per dm cube per second. Now we realize that for different reaction, the rate at which the product is formed differs. For this lecture, we'll focus more on this second graph. So how the product is formed. The graph of what? Um, Product formation. So we realize for some reaction they are fantastically fast. In less than a second, in a split second, they occur. Example, neutralization reaction. When the specific amount of acid is poured in the base, it neutralizes completely. So the acid and base are used up, then form salt and water. So in that case, we can focus the graph on the concentration of the salt formed. When the salt is it will have concentration. So while some reaction will take minutes, some will take days. In fact, some can take several months before they can occur. So what are the factors that cause all this variation? And that will lead us to occur the collision theory. So we are going to talk about collision theory and Arrhenius theory, or we call it the activation energy theory. So what is collision theory? So collision theory states that for a chemical reaction to occur or for a product to be formed, the reacting particles must collide effectively. So in short, before product can be formed, the reacting particles must collide, and the collision must be effective. If the collision is not effective, the molecules will bounce back and nothing will happen. So why is collision necessary? We've explained that in last class. Collision will allow bond breaking, and after that there will be what? Reorientation, and after that there will be what? Bond reforming. But first, most importantly, is that what? The bond has to be broken through what? Effective collision. Please write that down. So our collision theory focus on what? The collision, the frequency of collision, and the speed at which the particle moves. Arrhenius theory focus on energy. It talks about what we call the activation energy, and our last I made mention of it. Activation energy, symbol EA. So what does Arrhenius theory state? So it relates collision to energy. It states that for reactant to transform to product, the colliding particles, meaning the colliding particles of the reactant, must possess a minimum amount of energy called activation energy. So meaning if those molecules, colliding molecules of the reactant, if their energy, we can say their kinetic energy, which can link to speed and frequency of collision. If the kinetic energy their kinetic energy is not up to the minimum required energy called activation energy, the reactant cannot transform to product. And it went further to give us the relationship between the kinetic and the rate of what? Chemical reaction and activation energy as this. So this is what we call the molar gas constant from gas law. This is absolute temperature, and this is activation energy. This is the rate of chemical reaction, and that letter A stands for what we call the pre-exponential factor, or we call it the collision factor. So A is collision factor. So in this theory, it linked, if you have a temperature, we can link temperature to kinetic energy. So that we know that temperature is the measure of average kinetic energy of what? Of gas molecules. So we can say the more the temperature, the more the kinetic energy. The more the kinetic energy, the more the activation energy of the colliding particles. So it even showed a particular distribution. In this distribution or graph, it shows how the number of reacting particles with effective collision increases with increase in temperature. But before that, note this. For every kind of chemical reaction, there is a specific value for their activation energy. It is constant. Although under certain conditions, it can be lowered. Now let this graph represent number of reacting molecules or particles, and let this represent their kinetic energy. So we are going to have something like this. This particular distribution, it's not touch X. So this is the distribution for a particular reaction, and let's suppose the initial temperature is T1. Now let's suppose the activation energy is this. So this energy here is the activation energy. So it means all the molecules here, their energy have not reached activation energy. So the collision of these particles will not yield any product. But all these particles beyond this, from this activation energy to the front, they have what? Effective what? Collision, meaning they have the minimum energy required. What happens to the number of what? Particles if the temperature is increased? So the distribution will change and we are going to have something like this. So initially, this is the amount of particles, whose energy is either equal or greater than the activation energy. But now, when the temperature is increased from T1 to T2, so the number of particles whose energy surpasses the activation energy will have increased. So this is our activation energy. Let's trace it up. So if you compare, initially this is what we have, this region. But now the region has increased. The region has increased. So meaning if the temperature increases, the pathway will change, and in that case we are going to have more molecules whose energy will surpass the activation energy. This particular equation is very useful. So anytime you want to determine the activation energy of a particular reaction. So to do that, what we are going to do is we are going to measure the rate of chemical reaction at the certain temperature T1. So when the temperature changes to T2, we can look for the rates again. So we have two rates for two different temperatures, and from that we can make EA the subject because it's a constant. So to explain the reason some reactions are very fast and why some are very slow, we have three factors. So the first one is what? Collision theory, which says there must be collision. And the more the collision, the more the rate, and the more the effective collision, the more the rate. So first is the effective collision. Secondly is the energy of the colliding particles. They must have sufficient energy. And thirdly is the activation energy of that particular reaction. And the condition is that what? The energy of the colliding particles must be equal or greater than the activation energy. So apart from this, there are other factors that affect the rate of chemical reaction. And stylishly we've mentioned one here, which is temperature. This is what? Temperature. So number one, right, factors that affect the rate of chemical reaction. Factors that affect the rate of chemical reaction. So first, increase in temperature will increase the rate of chemical reaction, right, please. Increase in temperature will increase the rate of chemical reaction, and decrease in temperature will decrease the rate of chemical reaction. And why? That's so easy. We can use this collision theory and Arrhenius theory to explain. Why? If we increase temperature, the rate of collision too will increase. So secondly, the energy of the molecules will also increase. So meaning they will easily overcome the energy barrier or the activation energy. So that is why we sometimes store food in the freezer. If you prepare food and you cannot finish it, you cannot consume everything at a particular time, so you can put it in freezer for several days and it will still be okay. What are we doing there? We slow down the rate at which the food decay, because in food there's chemical reaction. We can link it to microorganisms feeding on it. So if the temperature is very low, it is slow. So now let's say this graph at which that represents the reaction taking place. So let's say normally this is where the reaction reach completion. This spot is where it reach completion. When temperature is increased, what happens? It will reach completion very quick. So we're going to have a graph like this. So it reach completion before its normal period. So this one that is steeper, it has higher gradient, shows that the reaction is faster than normal. But if the temperature is decreased, what happens? It will not get to end quicker. So it will take another pathway which is extremely slow. So it will get to the end before. So this is the normal level, let's call it X. But if the temperature is increased, it will be faster, then it will stop before X. And if the temperature is reduced, it will be slower and it will stop after X. It is slow. This for slow reaction, this for fast reaction. That's how temperature affect the rate of chemical reaction. Let's take other factors. We've explained number one, temperature. Number two, we can say concentration of the reactant. Concentration of the reactant. For gases, we say pressure of the reacting species. So we use pressure to describe gas. Concentration for what? For solution. For the first one, we said the more the temperature, the more the reaction rate. So the more the concentration, the more the reaction rates. The more the pressure, the more the reaction rate. Question is, why will increase in concentration increase reaction rate? Now, always note, to increase the reaction rate, the collision must increase. So if we have, let's say, few molecules here in this, entire space. Now, for the same space, if we have more molecules, what happen? For this one, the collision will be lower than this. Why? Because here they are little space. The space here is little, so the molecules are closer. Then they can collide more. So if molecules are confined in a smaller space, or more molecules are exist in relatively larger space, what happens? The rate of collision will increase. Hence, the concentration will also the rate will increase. Why? The concentration has increased. So suppose for this particular reaction it gets completion here. Let's suppose the concentration there is let's say 1 mole per dm cube, 1 molar. If the concentration is increased to, let's say, 2 molar, we are going to have a graph like this. It will reach completion faster. So this one is, if it's increased to 2 mole per dm cube. If the concentration is decreased to, let's say, 0.5, we are going to have something like this. It will get completion very slow, late. So meaning, if you want the reaction to increase, the rate of reaction to increase, you have to increase the concentration. The one with the highest concentration will reach completion first. The one with the least concentration will reach completion last. So concentration is very, very important in increasing the rate of chemical reaction. And same goes for pressure. So the more the pressure, the more the pressure, the lower the volume. For example, here we have these molecules here. If the pressure is increased, it means the volume will reduce. As you can see, the parts are closer. So in this case, what happens? The rate of chemical reaction will occur. The more the pressure, the faster it will occur. The lower the pressure, the slower it will occur. The next one is surface area. We use surface area to describe, solids. But for liquid, we use what we call miscibility. So, what is area? Now, let us consider the reaction between marble or limestone with hydrochloric acid. For this particular one, we'll be having calcium chloride, water, and CO2. So CO2 will be given out. So if we are to, show the relationship or how fast CO2 is evolved in two cases. So we want to know the rate at which CO2 is formed. So let's hold this in marble. And we throw this in this acid. CO2 will evolve, and the volume of CO2 that produced goes this way until it becomes constant, showing the completion of reaction. So now, what next? Let's break this down into pieces. When we break this down into pieces, what happens? The surface area has increased. So if this marble chip or this limestone is poured in this acid, we notice that the rate at which this reaction reaches completion will be faster. So you have something like this. So this was the initial, see where it reached completion. So the rate is faster. What happens if we use powdered limestone? If we use powdered one, what happens? It has much larger area. Then at the end we have something like this. So the one with the highest surface area reaches completion first before others. So meaning the more the surface area, the higher the rate of chemical reaction. The question is why? It is because By increasing the surface area, there will be a greater contact, which will be very easy. Greater contact between what? The reacting particles. So for example, if you use solid marble, for example, the area which this atom will get contact with this will be low. But the more we cut to pieces, it increases the area of contact. But for liquids, for example, for liquids, especially for liquids that I cannot mix easily, for immiscible liquids, in order to increase the rate of chemical reaction, we need to shake them vigorously. So by shaking them, what happens? If you shake the reactive particles, the area of contact will increase. So, which in turn will increase the rate of chemical reaction. Please note all this. You can write them down, draw them, then move on to the fifth one, which is the presence of a catalyst. Now, presence of a catalyst. So suppose we have this particular chemical equation. Determine the composition of potassium triisochlorate 5. So what happens if heat is supplied? This triisochlorate will decompose and oxygen gas is going to be evolved. So as usual, from 0 we are going to have oxygen we produce until it reaches its maximum value, showing completion. The rate volume of oxygen produced. But to able to achieve this, we need to apply a high amount of heat. But we realize that if we add a catalyst, in this case MnO2 as a catalyst, especially if this catalyst has large surface area, so we notice that this reaction will occur very quick. So instead of us having this, I'm going to have this. It's reach completion faster compared to this one. Why? Because this catalyst increases the rate of chemical reaction. But the question is how? How it doesn't increase the temperature. It has nothing to do with concentration or pressure. Although we increase surface area of the catalyst to increase its efficiency, but it is not part of the reactive particle. So how? So note this. Catalysts. This is a very important point. Catalysts increase the rate of chemical reaction by decreasing the activation energy following a new reaction pathway. So the way they increase the rate of chemical reaction is to decrease the energy needed, to decrease the activation energy needed by the reacting particles, so that they don't need to reach that energy they need before it reach completion, before the reaction reach completion. So now let's show how it happens for both exothermic and endothermic reaction. In our last class, we drew the energy profile for exothermic and endothermic reaction, and we showed the activation energy. So let's see how catalysts look for shortcuts to decrease the activation energy for the two. So the first one is endothermic. Why? Because the heat of reactant is more than the heat of product. So this is the enthalpy change. In this case, it is negative. But our focus is here on the activation energy, which is the energy between the reacting particles and the activation or transition state. So this is the activation energy. So this is endothermic because the heat of the reactant is less than the heat of product. So the heat of product is more. So this is the enthalpy change. And in this case, it's going to be positive. And what is the activation energy between the reacting, particles and the activation complex? So this is the activation energy. So what catalysts do is to follow a new reaction pathway. So this is the new activation energy. So what happens? The new activation energy is lower than the initial activation energy. Same thing goes for these two. A new reaction pathway just to lower the activation energy. So this is the new activation energy, which is less. So catalyst They increase the rate of chemical reaction by following a new reaction pathway to decrease the activation energy, and this happens for both exothermic and endothermic reaction. This is positive, this is negative. This is the activation complex. So you can be asked to draw the energy profile for a catalytic exothermic reaction, or the energy profile for a catalytic endothermic what? Reaction. So whenever you hear the word catalytic, it means after you draw the normal reaction pathway, then you draw another pathway the catalyst will create to lower the activation energy in order to increase the rate of what? Chemical reaction. Okay, please note all this while we go to the last point, which is the presence of sunlight. The presence of sunlight. So some reaction, the presence of light affects the rate of reaction. So we call them what? Photochemical reaction. So when a reaction is affected by light, they are called what? Photochemical. So there is an area in chemistry, we call it photochemistry, but that is beyond the scope of this class. You do that later in advanced level. We've done thermochemistry, which is our last class. We've done electrochemistry, we can call it, where you study electromotive force and so electrochemical cells and electrolytic cell. Then we are still going to nuclear chemistry. But for now, let's talk about photochemical equation. So photochemical reactions are reactions that are affected by the presence of light. For example, the reaction between hydrogen and chlorine to give us HCl. This reaction normally is fast, yes, because the entropy here is high. So it's fast. But in the presence of sunlight, it is explosive. So that is why anytime this experiment or this particular reaction is to take place, it is better it is done in a dark room or in a place where the light is not really much. But in the presence of sunlight, it is explosive. So meaning it is highly what? Photochemical or highly photodependent. Next is the reaction between methane and chlorine. So methane and chlorine. So in the presence of light, the reaction is very fast. So initially we are going to have chloromethane, and if you continue, we are going to have dichloromethane, then we'll have trichloromethane, and lastly tetrachloromethane. From the production of chloromethane to dichloromethane, trichloromethane and tetrachloromethane, this occurs in the presence of sunlight. If not, the reaction will not reach completion. It will reach completion but very slow. So in short, this reaction is initiated by light, usually the UV light. So, and normally what this does is to split the chlorine molecule into radicals after absorbing this light, and this is what drives the reaction. It creates like a spark that drives the reaction. Number 3 is also is what we call photosynthesis. Photosynthesis is a chemical reaction that occurs in plants, and the presence of light increases what? The rate at which oxygen gas is evolved. So photosynthesis is also a photochemical reaction. Another example is the decomposition of hydrogen peroxide. So this also will be fast in the presence of light. So for this to decompose, we need light, or we can also use catalyst. So to speed up the rate at which it decomposes. So to use catalyst, we either use manganese oxide, or we can also use potassium iodide, or we can use catalyst enzyme. So this catalyst enzyme is found in living organisms. So we then use this catalyst to speed up the decomposition of what? Hydrogen peroxide to water and oxygen, or simply the presence of what? Of light, because what this light will do is to, is to initiate the spark so that the combustion can occur. So I believe with this, we've come to the end of the rate of chemical reaction. You already know why some reactions are fast, why some are slow through the equation theory and Arrhenius theory, or we call it the activation energy theory. Then the factors that can speed up further the rate of chemical reaction, there are 6 numbers, and which we've explained them and how they affect or how they change the rate of chemical reaction. So in our next class, we go back to a reversible reaction, like I said, so chemical equilibrium, where the free energy is 0. See you in my next class.